So in my textbook, this is 10 for restoring forces and Hooke's law. So whenever we work with any kind of spring, the spring follows a certain particular law. Springs are elastic materials, so there are a lot of elastic materials around us. Some of them are more elastic than others, so we can see the level of elasticity because they compress or relax. If you take a hard object like a solid surface, you don't see much compression or relaxation, but if you take a spring, you can stretch it or compress it. And so in the process of stretching or compressing, we can look at types of forces that act on the spring. Let's consider a spring of spring constant K lying on a smooth surface as shown below. The surface is smooth, so we are going to assume there is no friction acting. So this is the spring. We have a mass, let's say a mass m at the end of the spring. So we can say that this point here is the reference point, where we can say that this is x initial. Later on, we shall say x initial is equal to 0. Let's say that now, x initial equal to 0. Okay. And then, so this is relaxed. Let's put it somewhere here. So this is the relaxed spring. Suppose we stretch it a little bit to a certain point here. So let's say that this is the displacement delta x. Okay, so this will be x final. Okay, this is stretched. Before I write stretch, let me move this a little bit down. So when we stretch it, we apply a force, let's say F subscript A, and so the spring, of course, is pulling back on the mass. So this is F subscript S for force of the spring. And then we can do a compression. So again, this is our reference point, and we've compressed it the same amount. Let's say it's delta X. Okay, so this is the applied force to compress it, and the spring applies a force the other way, Fs, like that. So this is compressed. So we can look at some of those scenarios. So we can apply Newton's third law. We see that the force applied is equal to minus the force of the spring, and this is true in both scenarios. So if you stretch the applied force in the right direction, on the first case, and it's positive, the force of the spring is negative. So anytime you apply force to the spring acts in an opposite direction to you. So we see that the applied force F subscript A is always opposite to the spring force F subscript S. Okay. So this is true whether you are compressing or stretching the spring. Also, the force applied is proportional to the displacement of the spring. We can remove the proportional sign and put in what is called a constant of proportionality, K, and we introduce an equal sign, so we have delta X, where the constant of proportionality K is called the spring constant. So if we want to write this in terms of the spring force, we will see that the spring force is therefore equal to minus K delta X. This is what is called Hooke's law. So the spring force is equal to negative K delta X. So whenever you stretch the spring, the displacement is opposite to the direction in which the spring acts. And when you compress the spring, the displacement is opposite to that direction. Okay. So we have two things going on. The applied force is proportional to the displacement, and the spring force is proportional to negative displacement. So this is Hooke's law. Any questions at this point? So let's do an example on this before we go on. Okay, so what is the displacement of the spring in this case?
The correct line is 5,000.
5,000 newtons. Okay, who has an answer for the displacement of the spring? 200? Oh, 20, okay. 20, what is the unit? Meters. What?
5,000.
5,000.
Oh, okay.
5,000 newton.
It's 500.
Oh, okay. So it's what is the? So you got 2.
Yeah.
Okay, yeah, 20. So the applied force is equal to K delta X. So delta X is just equal to F over K. So 5,000 divided by 250. Okay, so 20 meters.